In here, we will talk about some important question about Arrhenius equation and also one question for the special experiment iodine Koch reaction. Here I give you a graph for Arrhenius equation, which is supporting L and K and 1 over T. Then obviously we can do something to do a calculation and then find the active phase energy. And obviously it's like relative slope. So first point is we have to identify slope first. Then we can pick, technically we can pick any coordinate in a line. So maybe I use this one and also like this one. So at least the y-axis will be like minus 1.3 minus negative 1.6. Then the x-axis here will be like around 7.65 and here is like 8.15. But the other than 8.15 and 7.65, an important hint is here. 1 over T technically should be a really small number because temperature in terms of Kelvin, they usually should be so high, like even 25 degrees are really 298 Kelvin. So in terms of Kelvin, it should be like at least like 300, 400 or maybe even higher. So 1 over T reversely, it should be a really small number. But then why here is like 7 or 8, then the main point is like here is not 7.65, it's 7.65 times 10 minus 3. And also here is like 8.15 times 10 minus 3. So there will be an important trap. They may put the 10 minus 3 in the axis. That means the real change in x, it should be like that. Then obviously we can solve this equation easily. Then you should get the value is $600 and it's like minus 600. And then just as I said, like slope is equal to negative A over R. That means we can just multiply this one with R, which is 8.31. Then we can have the 4986. And then here, the unit will be joule per mole. Whenever we're using R, then the unit is like joule per mole. And then the minus sign is already cancelled out by the minus sign here. So the answer of the active phase energy will be just here. And then for second case, they ask you draw another line and then based on you adding a new catalyst, then obviously we can write something about that change of the catalyst first, which is like they will provide alternative reaction pathway with a lower EA. So here is already kind of the standard answer. And then the lower EA, then based on the slope that we learned, that we calculate from above, is equal to R. So the slope it should be increased also. Or you can say technically it should be less negative. Because the value of the top is like smaller, then the value of slope should be smaller also. That means when we draw a line, then you should draw something more horizontal. That means we have a lower slope. Then technically we can draw something like that. Then yeah, then obviously in the real exam, then you can using a ruler to draw a like obvious straight line. Just using a hand to draw it. Therefore you can see here, other than just some calculation, you have to also understand if you change the catalyst, if you add the catalyst, then the active phase energy may change. Then the line will also change into a lower slope or higher slope. Just like they can ask you a further thing is like, if I change the catalyst into a less effective one, then less effective one, that means the active phase energy should be like higher because the reaction rate is lower. That means you have to draw a line with a much higher slope. I mean the magnitude. That means the more and more negative. Then the line should be steeper than the original one. That means something like that. So if he is representing two different cases. Effective, then he is already another direction, something less reactive, less effective. I mean, then other than graphical calculation, another type of case will be here, and then you can see like no graph in here, and then they just told you some number. So here will be kind of just an algebra correction. Then based on the number that they told you, you have two different temperature. And then if you have two different temperature, then you think already you have two different 1 over t. That means you are setting up two different equation. Then when we put the equation here, that means ln for this one equal to ln A minus EA over R, and then 1 over 700. Then the new one, which is ln K, the unknown, and then ln A. And then here will be 1 over 900. Then when you have two equations, then based on your math, then you can do a simultaneous equation to solving. And then obviously in here, we can do something called like the 1 minus 2. Then the left hand side should give you this one. And then the right hand side, the RNA and LNA, and the second one should be the same thing because they are representing for the same reaction. So the both equation having the same magnitude of A, so they can cancel out. And then from this one, then based on we know the unit of EA, you know the number of EA already, and then we can put it in and then solve. But then just before solving, it's important simplify here. You can do something like that, which make your solving easily. Even though this time you're not solving EA, you're just putting the value of EA. But it just next time maybe they ask you to calculate the value of active free energy, then you know the solving, you can like have a common factor like that, then you can have your solving much more easily. And then obviously left side, you can just punch in the number to solve ln 2.42 times 10 minus 3, then which is 8.8376 times 10 minus 4 minus ln k. And then the right side, you can have 1 over 900 minus 1 over 700, and then over 8.31, and then times EA. And remember that here is joule per mole. That means the value of EA is no longer 178. You should put in 178 times 1000. And lastly, then 8.876 plus 4, then adding 6.7999, then you should have this, and then e to the power. That's why you will have a much larger value of k, which is 800 something. Yeah. So here will be like how you can calculate for the rate constant, or solving, even you can using this idea to solving the active phase energy based on you have two different equations, and then you can just do a simultaneous equation solving. Then lastly, here will be related to a real experiment for iodine Koch reaction. And then in the first line, they already told you some here. So that's like you have F2O8, and then adding I minus, and then form I2, and then SO4. Then based on what they told you, then you already can form the equation like that. And then based on the I, then you have to balance it, and then the sulfur. So actually the balancing is not really difficult. Yeah. And then for this reaction, technically they want to investigate the change of iodine ions on the ray, and then they have adding a starch to the mixture, because starch, remember one thing is like, even you may not studying bio, but then at least for this topic, at least you have to memorize one thing is like iodine and starch, they can combine and then to form a blue black color. Someone may call like deep blue or like black or just blue, but then it is like some color like that. and then just based on iodine and starch, they will combine. And then obviously they can measure the time taken for the reaction mixture to form those blue-black color as a kind of a measure for reaction rate. Because for the time taken, if it's like longer, then representing the rate is lower because they took a longer time to form that amount of iodine to make the color change. But they just here, other than potassium iodide, which is the Ki, other than potassium persulfate, which is the S2O8, they actually were adding one more thing in the mixture, which is sodium thiosulfate. Then in here, they haven't give you any information about sodium thiosulfate. I mean, like how they can react. Then they actually want you to know one thing is, whenever you see thiosulfate, which is S2O3, they can react with I2 and then to form Arrhenius and also S4O6. Then obviously the change in thiosulfate into S4O6 is not really important. But then you can see if thiosulfate are present in the mixture together with persulfate and also iodide, then the iodide that you form can react to thiosulfate and then form I minus. So they come up in here again. So here, already kind of forming a cycle from I minus to I2, and then they can form I minus again, and then they can go back to here. So they kind of forming a cycle. So technically, the color won't really change in a certain period of time. Because I minus to I2, I2 to I minus, so they keep on repeating the changes. So that means no I2 are free to react with starch and then give you blue-black color. So that's the whole theme of iodine core reaction. But then just at least if someone just asks you the final color, so it must be blue-black, because like at the end you should see some color change if they're adding starch as an indicator. But then just the time taken will be longer once you're adding thiosulfate. Then maybe some of you will think about like why the reaction will stop and then why there's color change. Why not just keep on repeating the change and then like I2, I minus to I2. Then the main reason maybe these two can be like just formed as a cycle, but then not this two. Because the thiosulfate or persulfate amounts must be limited. Then in this case, they technically want to investigate this reaction. So even though they haven't give you any number, but then just thiosulfate amounts must be very limited. That means thiosulfate should be used up first. Then when there's no more thiosulfate, then you don't have this reaction at this point. That means all the I2 form can react with the starch. That's why you think for iodine core reaction, most of the time the second equation is this one. That's why memorizing this equation will be like quite useful, and especially for like paper 3 or for like those exam board that haven't used iodine core as a correction, as a past period correction, which is I think OCR and AQA also like both of it having used iodine core to set up a long question to ask you. And then once you memorize the second equation, then the first equation is not really important. They just make something from I minus to I2. But then just when you know the second one, then the second one, the function of second one, just make the I2 into I minus again, so they can make the time taken for the reaction much longer. Because here was actually asking you like what's the function of sodium thiosulfate. If you don't have thiosulfate, then maybe the color change to blue-black still, but then just this color change will be like you can see this color change in like much shorter period of time. Then what's the main problem that you think is that if the time taken is like really slow, like small, maybe like 10 seconds or like less than 20 seconds, then the error for this time measurement will be like really big. And when you change it, and then when you increase the count of I minus, then this reaction will be like even faster, then will be like become much more difficult to measure the time for the color change. Then the experiment will be like really inaccurate. That's why most of the time people will put the second equation by adding thiosulfate, then they're making the time taken for the reaction much longer, which is having a more accurate result, as the percentage error of the time taken will be much lower. Then lastly, why did ions, that means the I minus here, is like considered as a no change unless they have changed color, because I minus reacted with thiosulfate, the con of I minus react with SDOH, the persulfate, using is like equal to the concentration of the I minus formed after I2 react. That means if you think the mole at both sides are equal, you react one I minus with persulfate, then technically at the same time you also form one I minus with the from the reaction with sodium thiosulfate already. So technically here you react one, then here you form one. Then the amounts that you react and then the amounts that you form is equal. So you can't see any change in I minus, in the concentration of I minus, because the mole is not change. So the concentration roughly is like remain unchanged.